Okay, so the first thing that I am going to show you is, or the first step would be to determine if it is ionic or covalent. So if we have a metal and a nonmetal, that means that it is ionic. Nonmetal, nonmetal is covalent. Now, I'm going to show you an example of both. And so I'm going to first do an ionic. And if you find that it is a metal and a nonmetal, then that means it's ionic and you need to draw electron transfer. So I'm just going to choose a random ionic compound. I'm going to choose MgCl2. And the first thing that you will do is you will have to draw the Lewis dot structures for both of them. And Mg is in family 2, therefore it has 2 valence electrons. Chlorine is in family 7, so it has 7 valence electrons. And then, since it's ionic, you are going to show the electron transfer. So this electron will go here, this electron can go there, and what you'll end up with is an Mg ion, magnesium ion, and since it lost 2 electrons, it will become 2+, and you have 2 chloride ions, each with 8 valence electrons, and each of them with a charge of -1. That is how you do an ionic. Now, in order to do a covalent, so let's say I have something like BF3. And that would be boron trifluoride. Boron is actually right on the edge there between metal and non-metal. It's a semi-metal, and so in this case, it's a semi-metal and a non-metal. The first step would be to draw the Lewis structure. So valence electrons, boron is in family 3, so it has 3 valence electrons. Fluorine is in family 7, so it has 7, and there are 3 of them, which means 21, so 24 valence electrons. Octet electrons is how many they want. Boron is kind of a weird one, and I didn't really explain this to you in class, but I'm just going to use it as an example here. But just for when we're looking at shape later, I chose this one. But boron actually is, we call it boring, because instead of wanting 8 valence electrons, boron will only want 6. So 6. Fluorine, we know, wants 8. 3 times 8, 24, plus 6 is 30. 30 octet electrons. Then bonding electrons will be octet electrons minus valence electrons, and that equals bonding electrons. And for octet electrons, it's 30 minus valence electrons, which are 24, which equals 6 bonding electrons. Number of bonds will be 6 divided by 2, which equals 3 bonds. Non-bonding electrons, that will be the valence electrons minus the bonding electrons. and that equals the non-bonding electrons. So valence electrons, we said were 24. Bonding electrons, we had 6, which means that we have 18 non-bonding electrons. So now, drawing it. Boron is the central atom because it is listed first, and I am going to put my 3 fluorines, one on each side. It said 3 bonds, so I've got that. Now I have to do 18 non-bonding electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Done. Okay, so now we have boron trifluoride as a image. Okay, or excuse me, this is the Lewis structure, not image. Lewis structure. Done. Step 1. Next, you will look at if it is what the electron geometry and what the shape is. So you have your boron, and you have 3 electron domains, and I drew it this way so you could see. If you drew it like you did on the last slide, that's fine. You can still see that there are 3 electron domains. Now, 3 electron domains right here, or regions as they call it on this. Then the next step is to see how many atoms are attached, and in this case it's 3. So our electron geometry will be trigonal planar, and I want you to note that these 5 are the only possible electron geometries. Then all of the rest of the names can be shapes. So the shape in this case is going to be trigonal planar as well, because of the fact that it has 3 atoms bonded to the central atom. Okay, so that's the second thing. The next step will be to look at the bonds and determine if they are polar or non-polar bonds. Bonds. Is it a bond dipole? Is it a polar bond? Same thing. Bond dipole means that it's an uneven sharing of electrons. Polar bond means it is an uneven sharing of electrons. So I don't know if you could see this very well, but fluorine is 4.0, boron is 2.0. So I am going to just mark one of them. And since all 3 are the same type of bond, I'm just going to mark one for ease and for neatness. And I'm going to show that that is a bond dipole. It has polar bonds, but the thing about it, we'll talk about that in the next step. So now if you happen to have something like this, okay, I'm sorry I didn't switch colors, but let's say you had this, okay, you would have to look at both the carbon-hydrogen bond and the carbon-chlorine bond. And carbon-hydrogen, carbon is 2.5 and hydrogen is 2.1. So that is not a polar bond. And if I have carbon as 2.5 and chlorine as 3.0, chlorine is slightly more, and so there would be a slight pull of electrons in that direction overall. And actually, if you were to look at that in terms of the carbon and hydrogen, there is kind of a pull. Now, one thing I forgot to add to the previous picture is that this would be slightly negative and this would be slightly positive. And the same case would happen here. This is slightly negative, and this is slightly positive for that molecule. So then the next step is to determine if it is a polar or nonpolar molecule. So let me draw it again. BF3. And it's not letting me do dots that easily, so sorry if it's taking me so long. There I go. I just kind of switched the size of the pen. Okay, so then we just drew the bond dipole bond, and we have 3 bonds, each is a dipole. Now, looking at this right here, so a nonpolar molecule does not have a dipole. A nonpolar molecule has only nonpolar bonds. Okay, we know we have polar bonds, so that doesn't apply. Or it has polar bonds arranged symmetrically so that the dipoles cancel out. That is the case here. We have an equal pull in all directions. So this is a non-polar molecule. Okay. Now, if I had something different, like let's say I had PF3 instead of BF3, I drew that prematurely, but you would have to do your Lewis structure process. P is in family 5. And it has 5 valence electrons. F is in family 7, and it has 7 valence electrons, so 26 valence electrons. Octet. Phosphorus wants 8. Fluorine wants 8. So 8 and 24 equals 32 octet electrons. And then bonding electrons, that would be the octet minus the valence. And so that would be 32 minus 26, and that is equal to 6, which obviously we see already that there's 3 bonds. So 6 divided by 2 equals 3 bonds. And then non-bonding electrons will be valence electrons minus bonding electrons. That equals the non-bonding electrons. And valence electrons are 26. Bonding electrons are 6. So that means there are 20 non-bonding electrons. So let's draw those in. So we've got 6 around each fluorine in order to give each fluorine octet, because remember a bond has 2 electrons. So that's 18. And then we have 2 more, so that's 20. Now, if we look at that in terms of shape, we can see that there are 1, 2, 3, 4 electron domains. And that means that the electron geometry is equal to tetrahedral because there are 4 areas. Then there are only 3 bonds, therefore the shape is pyramidal. And I showed you that on a previous slide, so I'm not going to go back. Bond dipoles, if I look at fluorine, it's 4. If I look at phosphorus, it is 2.1. So it's very clear that each of these is going to be a bond dipole. It is a polar bond. And then because you have the same pull in all directions, however, you have this lone pair, so it is not symmetrical. This is a polar molecule. Okay, so I went through all the steps with you again. So hopefully that helps.